All right, we have 7-1 today, a new chapter. In exercises 1 through 10, find the general solution to the exact differential equation. So we have to talk a little bit about the instructions. It says find the general solution. And they give you a derivative. So number 4, we have the derivative is equal to 1 over x minus 1 over x squared. They say x has to be greater than 0 just so that you're not putting 0 in the denominator and making the function undefined. That's the only reason for that x is greater than 0. As far as the operation of this problem, you don't really need to know that. It's just something that they need to add to cover all the bases. All right, let's talk about find the general solution. That means back up to the original function. There was a function whose derivative is this. What is that function? That's what they're asking you to do. That's what they're asking you to find. So we're going to multiply both sides times dx. These differentials, they work just like variables, so those cancel. And we have dy is equal to 1 over x. Now I know that I'm going to take the antiderivative of this, so we're going to write this as minus x to the negative 2, and then we have dx. If we're going to back up to the original function, that means we're going to integrate, we're going to find antiderivative. But just like anything else, you have to integrate both sides of the equation. You can't integrate just one side. So on the left side, we have the integral of 1. The integral of 1 dy is y. Go ahead.
For the 1 over x, why wouldn't that, like you do the antiderivative and it wouldn't be x to the negative 1?
What is the antiderivative of 1 over x? Natural log of x. Yeah. So if you do the x to the negative 1, you're going to add 1, you're going to get x to the 0, and that's the issue. That's the problem. So the antiderivative of 1 over x is natural log of the absolute value of x. We add 1 to the power. That's x to the negative 1, so we need plus 1 over x. The reason I don't have it as a minus is if we multiply by that negative 1, we're going to get that negative. Now this is a indefinite integral, so we have plus c. We don't have integrate from 1 to 7 or 2 to 10. Anytime you integrate with an indefinite integral when you don't have the values, you need plus c. You have to get that into your head. You need plus c. And the reason I stress it so much is sometimes AP assigns 1 point to that plus c out of 9. And so it's a pretty big deal. Go ahead.
Does the dx just go away?
Well, that's all part of, remember when we did the sums and we said, well, that is the height of all the rectangles and this is the width of all the rectangles? So really, when we do that integral, we're taking height times the base to find the area of the rectangles, and when you do the height times base, those numbers go away. So when you do the integral, that dx does is part of the process, and yeah, it does just go away. But you got to remember where we came from, where that came from. It came from rectangles. All right, that's the answer right there. So over on number 8, our very first step, when it says find the general solution, it means back up to the original function. We're going to multiply both sides by dt. Those cancel out. dy is equal to cosine of t e to the sine t dt. Now we're in this chapter, we're going to discover a process to actually find the integral of this. But this one, you don't even need the process that you're going to learn. Not for this particular one, I don't think. The integral of 1 dy is y. The integral of this is e to the sine of t plus c. Where'd the cosine go? Chain rule, right? So if you take the derivative of e to the sine t is e to the sine t, but then times the derivative of sine, times the derivative of the inside, which is cosine of t. So that's where the cosine went. It is not necessarily gone, but if I took the derivative, it would come back, right? All right, so that's part of the chain rule. Solve in exercise 11 through 20, solve the initial value problem explicitly. Solve the initial value problem. Solve. We don't really think of solving something as getting another equation, but that's what this is. When it says solve a problem, we're not looking for a number here. Usually the solution was like, negative 7. Well, that's not the case here. Solve now means go backwards and get the original function. So we're going to multiply both sides by dx. Those cancel, and dy is equal to 2e to the x minus cosine of x dx. To get back to the original function, we're going to integrate. And now y is equal to 2e to the x minus sine of x plus c. So we've gotten back to the original function almost. They give us some extra information. It's called an initial value problem, which means they give you a point on the original curve. Now, if they tell you specifically where this graph is, where the equation is, we can find the c. We can plug 3 in for y and 0 in for x. Now, you got to be careful because 0 doesn't always give you 0. E to the 0 is 1, so that part is 2. That part happens to be 0. But if that said cosine of 0, that'd be a 1. Cosine of 0 is 1, not 0. So don't automatically think you're going to get 0 every time you plug in a 0. That does not happen. Now we're going to minus 2, and c is equal to 1. So now we can go back to this spot right here, where we wrote the plus c, and we can fill in that c with a 1. 2e to the x minus sine of x plus 1. There's your final answer. So that is the function whose derivative is 2e to the x minus cosine of x and passes through the point 0, 3. All right, one more. Number 18 I chose. We're going to multiply by dt on both sides. And we get dx is equal to 1 over t minus t to the negative 2 plus 6 dt. And we have to integrate both sides to get back to the original function. So x is equal to natural log of absolute value of t. I have to add 1 to this. That's t to the negative 1. So that's plus 1 over t. I'd get the negative if I took the derivative. And then plus 6t plus c, plus some constant on there. The derivative of a constant is 0. So that constant could be anything. But now it can't be anything because they've given us a point. They said that x is 0 when t is 1. Natural log of 1 plus 6 plus c. And the natural log of 1 is 0. So c is negative 7. All right, so we go back to where we wrote the plus c. X is natural log of absolute value of t plus 1 over t plus 6t, and then finally minus 7. We can actually find that c. Otherwise, you just leave it as plus c, like the ones above. Yeah, I figured my computer is on its last leg, I think. We're getting new ones in January. I can't wait. Construct a slope field. Slope fields are for equations that we cannot find the antiderivative of. But sometimes we're going to use examples where we can find the antiderivative, but if you're doing slope fields, don't worry about it. Slope field is, all right, well, if you can't take the antiderivative, that doesn't mean you're not going to know what the function could look like. And so here we go. We're going to write little tiny slopes on these points right here. And in between any 2 points, we could write an infinite amount of slopes. So this is just a kind of an example of what we could do. All right, so here we go, y. The slopes are based on the value of y. So if we look at this point right here, actually all 3 of these points right here, the y's are 2. So that means the slope on all of these are 2. There's a slope of 2. We make little tangent lines. Then along where y is 1, all of the slopes are going to be not quite as steep as the ones we just wrote. Then down at 0, where y is 0, all the slopes are going to be 0. And then down here at negative 1, all the slopes are negative 1. Now, they don't ask you to do this. I'm done. We're done with the problem. That's it. Then they might go on, like on the AP exam, and ask you, what does the curve look like that would pass through 0, 1? Well, we kind of follow these tangent lines. Now they're not asking you to do this, but what if they said now, solve the equation. We've done the slope fields, we've drawn a line through one of the points that we think the line would look like. What if it said solve? We would multiply both sides by dx. We divide by y, because I want the y's with the y's and the x's with the x's. We could integrate, and that'd be natural log of the absolute value of y is equal to x. But I like equations that say y equals. So this is the base of e. So e to the x, remember log's always equal to the exponent, so e to the x, y is equal to e to the x. Well, that's an exponential function. And exponential functions, they look like this when they graph them. So by following all the little slopes of the derivative, right, the slopes, we found a general idea of what the graph would look like, the original graph. And it turns out it's fairly accurate. It looks just like an exponential function. Now, we're not going to go through all that work for this next one. We're just going to draw the slope field. Here we go. The slope field, all the little derivatives, all the little slopes are based off of x and y now, not just y. So let's start up here, I don't know, top right-hand corner. That's the point 1, 2. So 1, 2. Plug in 1, we get 2 minus 2, 0. So the little slope right there is 0. And then this is tedious work, but it kind of draws a picture of what the graph could look like when you're done. But it's tedious. 1, 1. 1, 1 is 2 minus 1, 1. So we have a slope of 1. And then 1, 0. So 2 minus 0 is 2. So getting steeper now. And 1, negative 1. So 2 plus 1, 3. Getting a little steeper even. There we go. Once you get to 3, 4, and 5, they all kind of look the same. But the half, a half, a 1, a 0, you can definitely tell those. All right, now we're going to the next column. Tedious. 0, 2. So that's negative 2. Slope of negative 2. Boom. 0, 1. Negative 1. So that's a negative 1. 0, 0 is 0. I know that one. And then 0, negative 1. Well, that'd be 0 minus negative 1. That's positive 1. So now the slope is positive 1. So we got one column left. Away we go. So we got negative 1, 2. So negative 2 minus 2. That's negative 4. That's really steep negative. I don't know how I draw negative 5 now. It'd be very similar. Be a little steeper. I can't draw it vertical, but just, I don't know. We just do the best we can on this. Negative 1, 1. Negative 2 minus minus 1, positive 1, right? Negative 2 minus 1. Negative 3, so getting less steep. Negative 1, 0. Negative 2 minus 0, so negative 2, like that. And then finally, we get to the last one. Negative 1, negative 1. That's negative 2 plus 1, that's negative 1, right? Like that. There we go. And we could probably come up with some sort of curve. We could follow the curves. Now, if you extend this out from negative 10 to 10 and do a whole bunch of, imagine having thousands of these. You could pretty much draw the curve exactly. I mean, the more we have, the better the curve would be, and we could find out exactly what it looks like. So don't think about what the purposes of this with 12 points. Think of it with if a computer could draw 10,000 points. You know exactly what it looks like. You wouldn't need to. Anyway, that's the whole point. Let's shut this down.